stabilized in all low impedance busbar protection device. So the main idea of our busbar differential protection algorithms have already been implemented in the 7SS52, but of course they have been improved a little bit in the 7SS85. So now we will start. What means low impedance busbar protection? What means differential current measuring principle? Busbar differential protection is simply applying the first Kirchhoff's law. The first Kirchhoff's law means that the sum of all currents, the vectorial sum of all currents, is 0. In case of a busbar, it means we are simply summing up the currents of all feeder, of course also a coupler if we come to couplers, and in a healthy system, this sum must be 0. This has to be done before I get to mention, of course, for each phase separately, for each selective bus zone separately, and also in additional for the check zone. Nina will later, of course, explain in detail what means check zone. It is a stabilized differential current measurement system. We will learn what means this stabilizing. And we call it low impedance busbar protection. That's very important to know, in contradiction to the also quite famous high impedance busbar protection. As here in this principle, the impedance of the relay is low in comparison to the CD circuit. We have a tripping component. The tripping component is a differential current, and the differential current is the absolute value over all currents, over I1, I2, and IN, depending on how many feeders, couplers you have in your system. And we have the stabilization component. That's the stabilization current, sometimes also called the restrain current. It's absolutely the same, which is built and calculated by the absolute value of all currents, the absolute value of I1, the absolute value of I2, and so on. In our device, in all Siemens devices, we both using instantaneous values, momentary samples, and also filtered measurements for our algorithms. Whereas it's important to say the important algorithms are based on momentary samples, on instantaneous values, because they are simply faster. Before I go to the details, I want to explain we are starting every time very simple, and I guess most of you will say, okay, it's quite easy, very simple, but from step to step you will see it will become a little bit more complicated, really to understand really the problems of the busbar differential protection. First up, the stabilization current. We have, you see here, the black line, that's the calculated stabilization current, the calculated restrain current. But in our algorithm, we are using not directly the calculated stabilization current, this black one. We are using the so-called modified stabilization current. You can see it here. The modified stabilization current is the same like the calculated stabilization current as long as the stabilization current is increasing. But if you see, according to the sinusoidal wave, as soon the calculated stabilization current is decreasing, the modified stabilization current is decreasing only a little bit in a linearized wave form. And the reason is also to have a high stabilization current during the zero crossing of the sinusoidal wave. And every time if we are saying we are looking to the characteristics, and you could see we have on the y-axis the differential current, and we have on the x-axis not the calculated stabilization current, we have the modified stabilization current. And the device will trip. We say there will be in the stabilizing area if we are below the characteristics, and the device will trip if we are above the characteristics. And important, on the x-axis, we have every time to think about the modified stabilization current and not the calculated stabilization current. We will see later in the examples how important this is. Let's, for our imagination, how to think what's behind all this characteristic, let's have a look to some examples. We start with a small example. We have a simple busbar. We have only two feeders. We have one in-feed and we have one outgoing feeder. And it's very important to understand, we will see more examples in this way with only two feeders, that two feeders is every time the worst case scenario. Especially if we come to seed saturation. So example with only two feeders is the worst case example, and all others with 3, 4, 5 feeders are not as so important and not so difficult like an example with two feeders. Okay, we have here the characteristics on the left side. We have an operation point. Means we have, in the ideal system, we have 0 differential current. Sorry, sorry, I'm struggling. And then an external fault will happen. And what happens in case of an external fault within an ideal system, the differential current will remain 0. But the stabilization current, which is the sum of the absolute value of these two feeders, will increase. And you will see, let me see, so that's the normal operation. Then we have the external fault. That means stabilization current will increase a lot. Okay. Next example, also an ideal example. Let's look how an ideal bus fault will look like. We start once again with a small example with a strong infeed and an with a strong infeed and an outgoing feeder. And now we still have the operation conditional, means we have a stabilization current in the area of the operational current flowing. And now we have an ideal internal fault. That means that the in-feed current, I1, the differential current, is the same as the in-feed current, and the stabilization current is also the same. Means we have a fault on the fault line. Means with the stabilization factor K is 1, we have really an ideal fault. CT errors. What exactly means CT errors? So CT errors is mainly the inaccuracy of the whole system, mainly the inaccuracy of the primary current transformer, the inaccuracy of the secondary current transformer in the device, of the whole measurement acquisition system in the device, and so on and so on. And we have the stabilization current, which is also the same. So here we have, so typically, a small differential current caused by the CT errors, caused by the inaccuracy of the whole system. And this is of course also proportional to the stabilization current. Means if we have in parallel and external faults, means the stabilization current is increasing, and then typically also the inaccuracy will also increase. So means this so typically the flow of the CT errors of the differential current caused by the inaccuracy. CT trouble. Very important slide now. What means CT trouble? CT trouble means mainly we have lost one CT, lost a complete CT for all phases, or lost CT of one feeder only for one phase. It doesn't matter because enough differential current in one phase is enough to clear, to trip the whole system. And here, this means CT trouble, the loss of one CT will cause the differential current of the load current of the CT we lost. So we have here CT trouble, and now we come to one of our most important settings. So you see in our characteristics, we have here the minimum differential current. And the most important rule, the most important setting rule is that the minimum differential current threshold, you see it here in the characteristic, should be higher than the load current of the feeder or of the coupler with the highest load current. The reason behind is that the philosophy of busbar protection is that with one single trouble, with one single fault, it should not happen that you will lose a complete busbar by fault. So it should every time two criteria to prevent an unwanted trip of a busbar. And therefore, once again, this minimum differential current threshold should be higher than the load current of all your feeders you have in your system. So if you lose the CT of the feeder with the highest load current, you will not risk an unwanted trip. Of course, sometimes I forgot to mention this, the minimum differential current should be also lower than the minimum short circuit current. That's also very important. And we will see it when we come to the sensitive characteristic that sometimes we have a problem in a really zero resistive grounded system. Normally this is no problem. If we have a resistive grounded system, this may have a problem. We will come to it later. Okay, let's stay on this very important slide. But we say this minimum differential current threshold should be higher than the load current. But what happens if in parallel we have the CT trouble, we have during maintenance activity or anything else, we have lost the CT, everything is fine. We will have a differential current, but we will not trip because the minimum differential current threshold is higher. But if then, in parallel, we have an external fault, we would trip nevertheless. Because then, of course, this CD which have been lost would have bring more CDs which is missing, and we would pass the characteristic and we would be in the tripping error. And therefore we have one further very important setting, that's the threshold of the differential current supervision. And this threshold of the differential current supervision should be lower than the lowest load current of all feeders. Because if you lose one CD, you should be for sure above the differential current threshold, And via this differential current threshold, you can block your busbar protection systems in order not to risk a wrong trip of the busbar, because then in parallel you will have an external fault. Okay, very important. Also, the next thing is very important. Now we come to a very simple explanation of the desaturation. You will see that's a quite simple model. It will become a little bit more realistic in the next slides. We will start at operation point A. We call it the pre-fault operation point. Means the system is fine. We have a certain stabilization current, we have no differential current at all, and then we have an external fault which increases the current a lot. And then the stabilization current will increase and increase, and at operation point B it will come to a CD saturation. And you know, CD saturation means not only the primary CD is not able to follow the increase of the current, it will go to zero. The current will go to zero. This means we will not have only differential current. We will have differential current, and both the stabilization current will decrease. So that's what happened after point B. And at point B, we will come to C, and at C, maybe the CD saturation will stop, because we will go to the other direction of the sinusoidal wave. And then we will have a differential current in case of an external fault, which is a function of the CD saturation. And we have the stabilization current, which is the absolute value of all currents. But as already mentioned, if, for example, current I2 will be the current from which will saturate, this component will also decrease. And then whether we will trip or not depends on our used stabilization factor. In this very simple model, with a stabilization factor of K is 0.5, and trip may happen. It's not absolutely sure, but we have at least the risk of a wrong tripping. But with a stabilization factor of K is 0.65, we would be in the stabilized area and everything should be fine. So, time for a first sum up. We have, for our busbar differential protection, we have very low settings. We have two settings which are maintaining and cover CT errors, cover CT trouble, and also cover CT saturation. We have the minimum differential current threshold. Also think about the minimum differential current threshold of the differential current supervision, but it's not so for the busbar differential protection else, it's an additional supervision. And we have the K factor for the stabilization. Let's have some small examples. Once again, worst case. We have here a busbar example with a very strong infeed with a big CD, 2500 amps to 1, which we here call it the current I1. And we have a small outgoing feeder, which we call now the I2. And we have an external fault. And let's see, and you will see, next slide, that here we will see the current, of course, in a normalized way. So let's say here we have the 2500 amps is normalized value 1 here in this example. And we see this blue dotted line will not saturate, but I2 will saturate, that's its violet color, will saturate after about 60 degrees, which means so roundabout at 3 milliseconds in the 50 Hertz systems. Let's have a look according to these currents, how the differential current and the stabilization current will look like. So we will have the differential current. Here's this red line. You see before, if we start on the left side or at 0 degree, I2 has not saturated. So at the very beginning we have 0 differential current. You see it here on the left side, the red line, the differential current is 0. But when I2 saturates, suddenly the differential current jumps, and it will be, because I2 is absolutely 0, the differential current will be the same as I1. So it's similar to I1. The stabilization current, this you will see here this dark green line, the calculated stabilization current. You will see it, it's I1 plus I2. And you will see here, the calculated stabilization current will decrease as soon the CD saturations of I2 will start. And that's the reason also we are using, as already said, for our tripping criteria, not the calculated stabilization current, we are using the modified stabilization current. So here in this picture you see very good, and maybe also the reason why we are using the modified stabilization current and not the calculated stabilization current. So the stabilization factor with K is 1. And so here the tripping criteria would be that the differential current should be above the modified stabilization current, but with stabilization factor K is 1. Of course, we have absolutely no risk of any tripping, but unfortunately, with a stabilization factor of K is 1, we would also not trip in case of an internal fault. So a stabilization factor of K equal to 1 makes no sense. So let's work with more proper stabilization factors. Here we see here with a stabilization factor of K is 0.5, it could be critical. So at least 2 times the differential current is above the modified stabilization factor. This means a risk may happen, but with a stabilization factor here in this example, K is 0.7, we see everything is fine, we would not risk any trip. I have explained this very important criteria that the minimum differential current threshold should be higher than the load current of the feeder with the highest load current. In an resistive grounded network, typically this criteria cannot be fulfilled because of the resistive grounding, and phase to ground fault would lead to quite low fault currents, which are typically not above the load current. And in this case, in order not to risk a wrong tripping in case of a fault, we have to use the sensitive characteristic. So the sensitive characteristic should mainly used in resistive grounded networks. It will also not work because during the last week I have some discussion whether this can also be used for isolated systems, because also in isolated systems we have a current due to the capacity of the cables in case of a fault, but it cannot be predicted. So really the resistive, the earth fault characteristic should be used only for resistive grounded networks, not for completely isolated networks. In this system we have very low earth fault currents. So the differential current is less than the highest load current, what I have already said. We can work with this characteristic, but this characteristic should not be activated every time. So the sensitive characteristic should be activated by a second criteria, which is the indicator of an fault, of an phase to earth fault. And typically we are using here the displacement voltage. So we are measuring the displacement voltage. If we are detecting a displacement voltage, we will activate the sensitive characteristics, and then everything should be fine, and we are really also on the safe side. Okay. I hope the sensitive characteristic is clear. Otherwise, of course, you have the possibility to ask questions. Let's come to the details of the algorithms. We have 3 algorithms working in our device. And the criteria for the selection are the current magnitude, is the slope of the stabilization current, I will explain later, and it's also the fault location. I will also explain how we will detect the fault location. We have the very fast 1 out of 1 algorithm, which is invented for very high fault current. Very high fault currents where the desaturation may happen later. And here the typical tripping time is 7 milliseconds at the trip relay. These 7 milliseconds are for the centralized busbar protection and with the type F, the fast output relays of the Protect 5. But here really the 7 milliseconds are really from fault inceptions until the binary output of the device has been activated. We have the 2 out of 2 algorithm, which is for medium and low fault currents. And very important, the 2 out of algorithm is also responsible for evolving faults. And here's the typical tripping time with the same requirements I have explained before, are 17 milliseconds at the trip relay contact. And fast but not least, for very special fault conditions, for really very low fault levels, a little bit above the differential current threshold, and with high DC offset, with high DC components. And here, last but not least, quite slow, 27 milliseconds, centralized busbar protection, and so on. But we are speaking here really for quite low fault currents. So typically, you will not have the risk when the filter algorithm has to apply. We will not have the risk of burning any contacts anymore because it will clear only very low fault currents. Very high current faults will be typically tripped every time with a 1 out of 1 algorithm. The slope of the stabilization current means here really a jump of the stabilization current. We will come to later. So really the change of the stabilization current per time. So typically as the cycle time of the busbar protection is 1 milliseconds, means really the slope, the change of the stabilization current, the jump within 1 millisecond. The 1 out of 1 algorithm, we call it also the sub-cycle tripping. The characteristics is every time triggered and must be triggered by a jump of the stabilization current. For busbar faults, for internal faults, the tripping condition must last for only 1 sample. And this is really our most important algorithm, guarantees a fast trip of busbar faults. And if you use high-speed relays, our electronical high-speed relays, this 1 out of 1 algorithm can trip really a busbar fault within the complete time with 3 milliseconds. Very important for external faults, for high current external faults, where also a CD saturation may happen later. And here the 1 out of 1 algorithm is not very safe against the desaturation. The 1 out of 1 algorithm will be blocked. Okay, and for external faults, the CD must stay without saturation also for only at least 2 samples. And we will see it in the example. The 1 out of 1 algorithm takes advantage from the saturation-free time at the beginning of a period, at the beginning of a short circuit. So, 2 out of 2 algorithm and Fourier algorithm. Here, the tripping condition must be fulfilled for at least 2 successive half cycles. It provides a stability at heavy saturation and also for heavy transient DC components. Very important, that's cause for the 2 out of 2 algorithm, not for the Fourier filter algorithm, that the 2 out of 2 algorithm has to trip also involving fault. That means involving fault, a fault which started externally and after 10, 20, 30, 50 milliseconds or 100 milliseconds went from an external fault to an internal fault. That's an involving fault. And also for high resistive busbar faults. So now we are just before my favorite slide. Let's sum up before I will come to explain really the coordination of the algorithms. We have 3 criteria. We have the criteria A, which means that the differential current must be higher than the minimum differential current threshold. You see it here on the characteristics. That's this criteria A. We have criteria B. That means that the differential current must be higher than the modified stabilization current, not the calculated, the modified stabilization current, multiplied with the stabilization factor. And we have criteria C, which you can't see directly here at the characteristics, which means we have a jump of the stabilization current. It's an internal value that are detected from 1 millisecond to the next milliseconds. We have a very high jump of the stabilization current, and this jump of the stabilization current, we say that's criteria C. The coordination of the algorithm. So just listen to my words. Afterwards, you will see if you later in some months or days want to follow, you will see also the explanation on the right side of the slides. But now I try to explain you, and so just listen to my words. You have here on the right side of this diagram, you have the trip. That means you have the trip. It will be the trip of one phase of one selective zone, or it can be also the trip criteria of one phase of the checked zone. You have a trip, and you have 3 inputs. You have one input from the 1 out of 1 algorithm, that's red bars. You have the input of the 2 out of 2 algorithms, that's the green bars. And you have the input of the filter algorithm, which is the blue bars. And you can see each algorithm completely independent is sufficient to trip a busbar, a bus zone or the checked zone. Let's start now to the left side. We have criteria C. Means we have a jump of the stabilization. Thank you very much, Nina. That's a very good animation. We have here the jump of the stabilization current. We have criteria C fulfilled. And here, if I have really a a training with where the participants online, I ask every time, okay, we have the jump of the stabilization current. Is it now an external fault or is it an internal fault? And some guys answering it's an external fault, some guys answer it's an internal fault, and some guys are right, as hopefully also you. We have no idea. A jump of the stabilization current, criteria C, could be both. A jump of the stabilization current will happen both in case of an external fault and also in case of an internal fault. But let's have at the very same moment, at the same millisecond, if we have a jump of the stabilization current, and at the very same moment, are we in the tripping area or not? Is criteria A and B fulfilled? Here, this AND getter, which is where this criteria A and B comes in. If we have in parallel together at the very same moment a jump of the stabilization current, and we are in the tripping area, then we can be sure it's an high current internal fault. And we will immediately trip, that's this red bars, we will immediately trip according to 1/1 algorithm. If we have this jump of the stabilization current, and in the very same moment we are not in the tripping area, means the differential current is below the minimum differential current threshold, or it's below the differential current multiplied with the stabilization factor, exactly. I thought there's a wrong here, something in the slides. Then we are sure it must be an external fault. So jump of the stabilization current in the very same moment, we are not in the tripping area. Then it must be an external fault. And very important, now we have to block immediately the 1/1 algorithm and also the filter algorithm. Because maybe 1 or 2 milliseconds later, a CD saturation may happen. So if we have this jump and we have at the very same moment no differential current, we will block for 150 milliseconds both the 1/1 algorithm and the filter algorithm. Okay, but let's go through the other possibilities. We have no jump, we are simply in the tripping area. So the differential current is higher than the minimum differential current threshold, and the differential current is higher than the stabilization current multiplied with the stabilization factor. That means we are in the tripping area. And one threshold exceeding is enough. We will start the 2/2 logic here in this green way. So that means we will not immediately trip with the 2/2 algorithm. We will start a 2/2 logic, which will come in the next slide. And also in parallel, if not blocked, we have our filtered algorithm, which has also its own logic and can separately trip the busbar. Okay, and here that's hopefully the explanation I have given to you now, if you want to read it later by your own. Two-out-of-two algorithm. I have already explained one threshold exceeding is enough to start the 2/2 algorithm. Of course, but that's the same for the 1/1 algorithm, but as we have here in separate slide, we will start the 2/2 algorithm only if the differential current supervision has not picked up and if any measured value supervision has been picked up. But I think that's a separate topic we will explain supervision, Nina? Third or fourth tutorial, something else, at least later. Okay, one threshold exceeding is enough, and then the algorithm will start at that time. At that time of 8 milliseconds in a 50 Hz system, and for 6 milliseconds in a 60 Hz system. Why is this 8 and 6? This datetime must be enough to be sure in the second half wave of the sinusoidal wave. So the 2 out of 2 algorithm has to be ensured that we will trip only if we are in the tripping area for 2 succeeding half waves. So one threshold exceeding, we start at that time, and then after 8 milliseconds for a 50 Hz system, we are starting a 60 millisecond measurement window. It's only 5 milliseconds for a 60 Hz system, and within this window we must fulfill 4 threshold exceedings. If this is fine, we can say, okay, we are in the tripping area for 2 succeeding half waves. We will trip according to the 2 out of 2 algorithm. If not, we have to reset this flip-flop. And via this flip-flop, you would memorize whether this criteria is really fulfilled in 2 succeeding half cycles. So we will reset it. So with the next threshold exceeding, we will start at the very beginning. 1 threshold exceeding is enough, that time, and really only for 2 succeeding half cycles. And this will be ensured via this flip-flop, which have been set after the first threshold exceeding, and will be reset if in the next measurement window we are not fulfilling the criteria. Okay. Let's come to some examples with the things we have learned now. Let's come to an external fault without any CT saturation. We see here, it's quite boring, I guess. We see here the differential current is 0 because it's an ideal external fault. And we see the calculated stabilization factor, which is going to 0. And very important, only just to once again see you really on diagrams, on figures, what I have tried to explain to you. You see the modified stabilization current multiplied with the stabilization factor. That's this brown color here. And if you see the modified stabilization current multiplied with the stabilization factor, and in comparison the differential current, you can directly say if the differential current is above the modified stabilization current multiplied with the stabilization factor, you are in the tripping area or not. But this is quite easy example. We have no differential current at all, so nothing could happen. Bus fault, a little bit more interesting. We have a quite bus fault. We have here the differential current, which is also going to 0. And here we see once again, here now in white color, the modified stabilization current with multiplied with the stabilization factor. And now, once again, maybe you can answer by yourself my questions. Will here the 1 out of 1 algorithm immediately trip? You can think a little bit by yourself and answer. And the correct answer is you can't answer these questions because you do not know our internal criteria. You don't see any, how to say, on the y-axis, any how big is the nominal current or anything else. So simply you can't answer in this case whether we will trip according to 1 out of 1 algorithm or not. Let's assume it's seems like a not too big internal fault. Let's assume we will not trip according to 1 out of 1 algorithm. We will trip according to 2 out of 2 algorithm. So for the 2 out of 2 algorithm, we have learned 1 threshold exceeding is enough. We have this measurement window after 8 milliseconds, and then we have a measuring window of 6 milliseconds once again. And within this measurement window, we have to reach 4 threshold exceedings. Let's have a look. So 4 threshold exceedings, okay. We will trip here according to 2 out of 2 algorithm. Now, it become a little bit now to the end. Our examples get more and more complicated. You remember this example with a strong in-feed, 2500 amps to 1, and the small outgoing feeder with a small CT, 400 amps to 1 amps. We have an external fault with CT saturation after 60 degrees, after around about 3 milliseconds. We have the I1, the in-feed, that's white, looks a little bit like blue, but should be white, this big current. And we have a heavy DC displacement. We have a DC offset. You could see this in-feed current. We have a strong DC offset in the opposite direction. And we have the outgoing feeder. That's this brown color, which will saturate after around about 3 milliseconds. And now let's look again with this more realistic example, with this DC offset, how the differential current, how the modified stabilization current looks like. Here we have now in this diagram, the red color, that's the differential current, the white line is the stabilization current multiplied with the stabilization factor. And the most important thing for us is this brown line, which is a modified stabilization factor multiplied with the modified stabilization current, multiplied with the stabilization factor. And very important are in our algorithm, as already stated, are the saturation free time. Here you could see here during my animation by this, it was blue or green or rectangle, and now animated also by Nina with his mouse. Thank you very much. You could see we have here this differential for the first 3 milliseconds. The differential current is 0, and you see it here, the stabilization current. You see a big jump of the stabilization current. And now if you remember back to the coordination of our algorithms, what happens? We have fulfilled criteria C. We have this big jump, this high jump of the stabilization current. We do not know, is it an internal or external fault? But if we looking at the very same moment, whether we are in the tripping area, whether criteria A and B fulfilled or not, we can say now it's an external fault because we have the jump of the stabilization current, but we are not in the tripping area as the differential current is 0. So what we will do, we will immediately block the 1 out of 1 algorithm and also the filter algorithm. So these are this very important first 3 milliseconds, the saturation free time after an fault. Here, that's the next phase. Now we have the differential current, which is very high. And here, first time you see it, maybe Nina once again, where the differential current the first time is above, is in the tripping area. And we have learned here, now we have a 1 threshold exceeding, which is enough to start the 2 out of 2 algorithms. The 1 out of 1 algorithm has been blocked, but we will start here the 2 out of 2 algorithm. Here's the first time. So, and we see, now we will start the 2 out of 2 algorithm, but we have learned the 2 out of 2 algorithm, we have to be in the tripping area for 2 succeeding half cycles. The 1 out of 1 algorithm is blocked, but the 2 out of 2 algorithm has to be looked whether we are in the tripping area for 2 succeeding half cycles. So, first 2 periods, areas with differential current is above the modified stabilization current, but we have no trip by the 1 out of 1 algorithm. The 2 out of 2 algorithm will not trip. You can see here that's the period 1, and the second period will be this blue one, but here which would be the measurement window for the second half-wave of the 2 out of 2 algorithm, but here during this time we are not in the tripping area. Then once again we would start the 2 out of 2 algorithm in period 3 once again, but in period 4 we are once again not in the tripping area. So we would have no trip here in this case, whereas we are 2 times in the tripping area. So it's time to have a little bit water. What is missing? I hope you have now understand mainly the coordination, 1 out of 1 algorithm, blocking 2 out of 2 algorithm. What we have not so talked much about is the filter algorithm. So let's have here this small example of a busbar fault with a quite low current with the desaturation and a very strong DC displacement. Here we have this trip by 1 out of 1 will not happen because here you see on the y-axis the nominal current. The nominal current is in the maximum only 2, and this will for sure not trigger a 1 out of 1 algorithm. So the 1 out of 1 algorithm cannot trip, and the 2 out of 2 algorithm has also no chance. Here's a 1 out of 1 algorithm because we have, you could see here this little jump of the differential current, but which is still above the modified stabilization current. So for the 1 out of 1 algorithm, the fault current is simply not high enough, and for the 2 out of 2 algorithm, we are not in the tripping area for the second half wave. So only when the DC component is declined, so that's roundabout here in this example after 100 milliseconds, then the 2 out of 2 algorithm can be applied and will trip. But okay, also for a quite low fault current, a tripping time of more than 100 milliseconds is not so fine. And so far, I guess it was 25 years ago with the first RTTS test of the busbar protection. And then we invented additionally for this very special case, the filter algorithm. So let's have a little bit of look to the root cause of the problem. We have here the differential current, which you can simulate, for example, just to infeed one current into a bus zone, and then you will have a differential current. And we have the differential current threshold. And then if you add a quite high, you are only a little bit above the threshold, and you have a DC component. And then you will see that for the positive direction, it's no problem to overreach the minimum differential current threshold, but in the opposite direction, due to the DC offset, you will not reach the minimum differential current threshold. And that's simply the problem of the example before. Because of you are a little bit above the minimum differential current threshold, you have a DC offset, and the 2 out of 2 algorithm is looking to beat the tripping error for the 2 succeeding half waves, and then you have a problem. And what will be the solution? The solution will be a filtered algorithm which will eliminate the DC offset. I guess last slide. Here's a small example to show you a little bit the principle of the DC offset. We have in this first, please make it big, Gat. I need this, okay. Here the characteristic in the middle, that's K1, that's the measurement point. We once again only injecting in a bus zone only one current. And we have a strong DC offset here in the negative direction of the y-axis. And you see the differential current, which is the characteristics at the top. You see a very big differential current when the sinusoidal is really completely in the negative direction, and you have a very small differential current for the other half wave. And then once again you will have the problem. You will only be above the minimum differential current threshold for one direction of the sinusoidal wave. And what we are doing now, we are applying, you can see it here, the sinus-cosinus filters with some filter coefficients. But the disadvantage is, of course, you have a measurement window of these filters, and this measurement windows is coming from the past to the future. And you need a little bit time when all the sampled measured values which have been passed through the filters are completely in the measurement window. So this needs around typically 20 milliseconds, one cycle. But if the fault inception is completely in the measurement window, you will have a stable differential current, you will have a stable stabilization current, and you can make a stable decision whether to trip or not. It needs a little bit time, but then for sure. So we will have typical tripping time of 27 milliseconds. Sounds quite long compared to the 7 milliseconds of the 1 out of 1, but much better than the 100 milliseconds for the 2 out of 2 algorithm in this case.